Hi guys, it's Moses from the Mr. Benetti YouTube channel. I'm also one of the admins on the Facebook Electrostatic Machines group. I'm a member of Tesla Coils and High Voltage, and Tesla Coils Our Boss, and High Voltage Photography, and quite a few other groups on Facebook. As those who've been following me know, I've been wanting to put together a 12-inch Tesla coil to see if I can power it by my quadruple Benetti machine. And before I do that, I wanted to set it up and make sure it's all in tune and I'm getting decent output using a more conventional power supply. I chose to use my FlyBack transformer, my ZVS-driven AC FlyBack, to drive the thing just to see if it's working and if I got it basically in tune. In this big beige electrical box here, I have an AC FlyBack. It's non-rectified FlyBack transformer. You can see a big metallized film capacitor across the outputs of the ZVS. That's because the capacitance, the 0.65 or 64 microfarad capacitance that it comes with, is not quite enough to pump enough current through to drive this coil. I found 10 microfarad capacitor across it works just fine. I could probably go smaller. I've gone as small as an extra half a microfarad. It worked pretty good. For some reason with this metallized film 10 microfarad capacitor I have laying around, I get the best results, so that's why it's there. The ZVS driver is a cheap $8 Chinese, very simple ZVS driver that you see all over the place, and that's what I'm using to power it. Because the frequency of these FlyBack transformers is way too high to properly fill my 10 capacitors on each half cycle. I have to rectify the FlyBack. Now, I have a few commercial from old TVs and old CRTs FlyBacks that are already rectified, but I didn't want to take this apart. I just wanted to use this as is. So right here in this piece of wire over here under the black shrink tubing, I have two 30 milliamp 20,000 volt diodes connected in series because this thing is supposed to be able to produce 40,000 volts at 30 milliamps if it's driven to its capacity. So I figured two of them in series just to be safe. I probably should have doubled them up and done two pairs of four. Two pairs of two and connected in series just so I can handle more current. I have blown up a few of these diodes before, but it's working for now, and hopefully it'll work long enough to do this video at least. So that's what I'm using to power it. Right here in this metal box here is just a switching power supply, switchable voltage input from 110 to 120 mains voltage to 220 and 240 mains voltage with a little switch, just like a computer switching power supply. The output is simply 24 volts DC at a maximum of 10 amps. I do have bigger power supplies. I got another 24 volt power supply like this, but it's a 20 ampere. I also have a very large variable variac that I could use with a rectifier to power this, but this is more than enough to create flaming arcs when I'm just using the FlyBack by itself. Massive flaming arcs, and I don't need any more, so I'm sticking with that. It also happens to be the power supply I drive the motor on my motorized quadruple Benetti machine with. So it was around, it was here, and it's hooked up, and that's what we're using to power it. Now, normally when you create a tank circuit on a Tesla coil, you want to use a metallized film or polystyrene film capacitors made for resonance and made to run at very high frequencies and relatively high currents. They say stay away from ceramic capacitors unless they're the doorknob type used in radio receivers. Those are usable and good, but quite expensive. And they tell you to stay away from these, which are this is a 20,000 volt 1 nanofarad capacitor. I wouldn't consider using this because I need quite a few of them to get the capacitance I need. I need about 5 to 6 nanofarads of capacitance to make this work the way I have it set up, and I would need way too many of these. I could connect 5 of them together and I get my 5 nanofarads, but you want to have more voltage on your capacitors than you're putting out, at least double. So if you're feeding 20,000 volts in, you want to have at least 40,000 volts on your capacitors just to be safe, maybe even more. In my case, I'm using 20,000 volt capacitors. I have 3 of them in series to give me 60,000 volts. They're 10 nanofarads each, so that gives me 3.3 nanofarads theoretically. So I've got 2 of those connected together. Supposed to give me 6.6 nanofarads, but these I am using ceramic capacitors, and these are notoriously unmatched. Most capacitors are unmatched, but these are pretty badly unmatched sometimes, and I'm getting about 5.5, exactly 5.5 nanofarads out of my capacitors. I have, again, 3 in series, which gives me 60,000 volts, and I have 2 pairs of those series up capacitors connected together, a total of 6 capacitors, to give me 5.5 nanofarads of capacitance, which matches the primary I have on my Tesla coil. I need just under 16 turns. That's what I have there to match my primary to my tank capacitor setup. I've also got the capacitors in a food container that's been sealed with number 704, I believe it is, RTV. It's a little more liquidy when it's wet than the typical silicone is, and it's easy to seal cracks with, and it dries much stronger than regular. So it's the type of silicone you usually see a big gunk of white goop of that inside power supplies, holding down cables and stuff, and holding down various electronic parts, sometimes holding electrolytic capacitors steady on circuit boards and so on. So it's pretty robust stuff. I put that on top to seal it because I've got the capacitors buried in mineral oil, and the reason they're buried in mineral oil is because even though they're supposed to hold 20,000 volts, there's typically not enough distances between the leads on it to handle the 20,000 volts without arcing to themselves. So that's why it's in mineral oil, and I'll see if I can zoom in closer and let you see what that looks like. Here we go here. And let's see. So if you can see that in oil I have these, they're much bigger than the one I showed you. These are 10 nanofarad ceramic capacitors. Typically you don't want to use ceramic disc capacitors because they can't handle the high currents developed in a Tesla coil, and they can't handle the frequency. I had these laying around. I forgot to order the right kind of capacitors when I was putting the ordered for parts together. And I wanted to get this going. I figured I could probably use these guys and get something happening and change them later. And if I destroy them, I have 20 of these in the house, and I could always build another batch. So this is what I'm using, and they actually work. And the specs on these say that they can handle very high frequencies and handle very large overcurrents. That's what the Chinese specs say. I don't know if it's right or not, but so far it's working, and we're going to eventually be driving this hopefully off of the quadruple Bonetti machine, and they should hold up. In the meantime, I have time to order new ones. While I could test this while I'm ordering new capacitors. I also have these polystyrene film capacitors, which are the capacitors you want, not this type. This type over here is they don't handle the current that you would typically have, particularly on larger Tesla coils. They're not as robust as the little boxed epoxy potted polystyrene film capacitors you would use, or the long cylindrical like the Cornell Dubilier capacitors that are also polystyrene film, but much more robust. These things are not made to handle the current. The biggest problem with these is they physically very, very, very fragile. This wire, this center lead, this axle lead that you see coming out is not the lead to the capacitor. It's used as a lead to the capacitor, but there's a tiny little thread-like lead coming out on both sides hooked to these center leads. The center lead just gives it more robustness for soldering down and making connections, but they tend to break and they tend to snap off, and then you're left with a capacitor that's useless. But these would probably work better than what I have. The reason I didn't use them is I thought I only had 4 that work, which you see here. This gives me a total capacitance of about 3 nanofarads. that will work with this coil if I go up to, using the wire I'm using on the primary, if I go up to 23 turns. I have about enough for 21 turns, and I could probably barely fit 23 of that particular diameter wire on that core. I didn't have any more, so I'm going with the ceramics for now. I didn't realize that I had two of these that are perfectly good. They're hanging off my quadruple Bonetti machine right now, so I actually could solder those on here, so I have one more set. And then I'll get about 4.5 nanofarads, which is enough for the wire that I have for my primary. So that's our tank circuit. Normally when you see the a spark gap Tesla coil topology, there's two. One, the capacitor bank is connected directly across the primary, which is what I have done here, even though it might not look like it in the picture. That's what I'm doing. Directly across my primary is my capacitor, and I have the spark gap on one side of the primary connection. You could do the opposite. You could have the spark gap across your power supply and the capacitor on one leg of your primary. I have it the other way around for this video and for this purpose. And now we'll go back and see if we can get that coil back in view here. And we'll see what kind of breakout we have. Hopefully my high voltage diodes, I'm half-wave rectifying my FlyBack transformer, and the reason is because you don't have enough time between each half cycle running at 30 to 40 kilohertz that the thing runs at to possibly charge your capacitor bank up where it needs to be charged, so you have to rectify it. I'm intentionally half wave and not full wave rectifying it because I want to drop the voltage down lower so I don't over voltage my capacitor bank for a number of reasons. So we're sticking with simple half-wave rectification, and that proved to be more than enough. And now we'll see if we can turn this guy on and see what happens here. If we get any breakout, hopefully I can make it dark enough in here so you can see something impressive. Yeah, it looks like we're getting it dark enough. Turn this guy off. And now I'm going to turn on the coil. Can't see anything right now, but let's turn it on. See, it's working pretty good. It was working pretty good. You can see I caught my diodes on fire. They're not robust enough, obviously, to handle the current going through them. But as you can see, the Tesla coil was working. That's quite a nice plastic fire I got going on. Good thing I have my balcony door open because that's PVC and it's not good. But again, the capacitors work fine. Diodes not so much. But I'm gonna call this off for now and put this fire out. Bye guys. See you next time in the next part of this video.